Okay, welcome back Physics 30s to our next lesson. This is 2.8, and today we're going to be looking at the conservation of electrical energy. Okay, so we've talked about conservation of energy before, and we've stated that energy cannot be created or destroyed. This was the first law of thermodynamics. And we've written it like this, that all the energy initial equals all the energy final. And we also wrote it like this, where the sum of the potential and kinetic energy initial equals the sum of the kinetic and potential energy at the end. And if we put the kinetic energy on one side and the potential energy on the other, we found that the change in kinetic energy is equal to the change in potential. There should also be a minus sign there, that if the kinetic goes up, the potential goes down, and if the potential goes up, the kinetic goes down. So we've talked about this before with the potential energy of springs and gravity, and now we're going to look at it with electrical energy. And kind of like I showed last lesson, we can make the analogy here to a gravitational field with our electrical field. We said that if you are lifting a mass in a gravitational field, you give it potential energy. And if you move a charge in an electric field, you are getting potential energy there. Gravity was mgh, electric potential energy was QED. And now we're going to look at a moving charge, either releasing it from potential energy and it's going to accelerate, or firing it into a field where it's going to slow down and gain potential energy. So just like with the basketball, if we were to let it go from this position, it would fall and its energy would become kinetic just before it hits the ground. We could release that charge and it would accelerate away from the positive towards the negative and have kinetic energy at that point. Now, to have the charge either exit or enter the system, we're going to have a little slit or a hole in the charged plate like this. So if we had this positive charge on this side and maybe a proton on this side and we release it, it's going to accelerate, pass through the opening, and then continue at a speed once it has left those two plates. And we can have a lot of different scenarios. We could take the positive charge from outside, shoot it inside, and then have it slow down to a stop or even crash into the other end. And we could have this for a positive or a negative charge. So let's say that we take this negative and we actually shoot it with an initial velocity into this field, but because it's a negative, it's going to get repelled from the negative, accelerated towards the positive. So it goes in rather slow, but then it's going to repel, speed up, and crash into the other side. So we have any combinations of directions, initial speeds, and charges. So let's look at an example that says, what is the speed of the proton when it exits the plate? So I'm going to start with a proton. It's supposed to be all the way up to basically right on that positively charged plate. It's going to leave and it's going to fire out of this kind of like a gun of shooting this proton. So we want to figure out how fast it's going to go. So what we have to relate its energy in between those plates to its speed is relating its potential energy to its kinetic. So let's start by saying that our EI is equal to our EF. And then I'm going to write that same formula that we had from the first slide, where all my potential energy at the start plus my kinetic energy at the start is equal to my potential at the end plus my kinetic at the end. Now we're going to say that when it started, it was at rest, so there was no kinetic energy at the start. And once it leaves the plates, it's got no potential energy after that. So I can cross out those two terms. My EPI is equal to my EKF. Now if we're looking at its potential energy, we have two formulas. We have the EP is equal to QED, or EP is equal to QV. Looking at the first one, this has to do with the field strength. And we don't know the field strength, but we could figure it out from the volts and the plate separation between these plates. However, how I would get that is with the equation V is equal to ED. Well, what I've already kind of done with this equation over here is I've replaced ED with V. And we actually already know the volts. So we could use that first one, but then we're going to kind of end up going back the other way anyway. So I think we'll just use this one here. EP is equal to QV. So let's put that in there. QV is equal now to our kinetic energy. And that's the same formula as we saw from before, half mv squared. Now you might be thinking, well, isn't that 12 centimeters important? That's nowhere in this formula. Now it is good to note that if we separate those plates further apart, the field strength is going to decrease and then our acceleration will decrease. But then it's going to be accelerating over a larger distance, so it's going to cancel itself out there. If we're close together, there's a high acceleration for a small distance. If we're far apart, there's a lower acceleration for a larger distance. So it should not affect this equation, the distance of those plates, but we're basing it off of, again, the volts and the charge of the proton in this example. Okay, so now let's solve for V, V being velocity, not the big V, which is volts. So Q, this is a proton, so this is 1.6 times 10 to the negative 19 coulombs. I should rearrange here first, so times by 2, divide by mass, and square root. So let's take that charge and times by 2, then times by our volts, 12 volts, divide by the mass of a proton, which is 1.67 times 10 to the negative 27. Then I'm going to square root that whole term. I'm getting a number that rounds to 4.8 times 10 to the 4 meters per second. All right, so conversion from potential energy into kinetic. Okay, let's take a look at another example. This one, we're going to be shooting an alpha particle into these plates at an initial velocity of 5.2 times 10 to the 4 meters per second. And it says, will the alpha particle hit the other side? If so, how fast does it hit the other side? And if not, how far is it going to go? So we're going to shoot this particle in. Again, it's going to feel a repulsive force from that positive plate. We're going to figure out what's going to happen to it. So again, this is looking at energy. So let's start with EI is equal to EF, my kinetic at the start, plus my potential at the start is equal to my kinetic at the end, plus my potential at the end. Now we know at the start, when it wasn't in those plates yet, that it didn't have any potential energy, so I can cross that out, and it did have kinetic. Afterwards, we're trying to figure that out though. Does it hit the other side with kinetic energy, or does it stop only reaching a certain level of potential energy? So how we're going to figure out what scenario is going to happen is we have to look at its initial kinetic and figure out how much potential energy it would gain by going to the other side. If it has that amount or more, it's going to hit. If it has less than that, it won't make it all the way there. So let's start with this half mv squared and figure out that energy. So we have 0.5 times the mass of this alpha particle, 6.65 times 10 to the negative 27 kilograms, then times by the velocity, which was 5.2 times 10 to the 4 meters per second, and we'll square that number. And I'm getting 8.99 times 10 to the negative 18 joules. Okay, so now we have to figure out the potential energy that would exist in going that far through those plates. So how we could find that, again, is EP is equal to QEV, but we don't know the field strength. We do know the volts. So I think the easier equation here would be EP is equal to QV. So let's figure that out. Charge on the alpha particle is plus 2E. So that's going to be 2 times the elementary charge, 2 times 1.6 times 10 to the negative 19 coulombs, then multiplied by the voltage of 60 volts. And that gives us a much bigger number of 1.92 times 10 to the negative 17 joules. Okay, so that's a lot bigger than the amount of kinetic energy we have at the start. So we won't have enough energy to get all the way until the end. So I'm going to cross that out. We don't need to figure out how fast it's going to hit, but we want to figure out how far it will go. So now to solve this, I'm going to say all our kinetic energy gets turned in potential, not enough to get to that side. So my answer isn't this. That's if it got all the way to that side, have that much potential energy, but it's going to get somewhere in between. So let's say that our kinetic energy is going to turn into potential energy because it's going to stop, and we're looking for where it's going to stop. It's going to go back the other way after it stops, but we're looking at where it stops. So let's write half mv squared. Actually, I already have that number calculated. 8.99 times 10 to the negative 18 joules is equal to our potential energy. Now you might be thinking, can I just put in QV like we did before? And we could, but we don't have the V. You might be thinking, well, it's right there, 60 volts. But that's based off of that plate separation of 15 centimeters. This mass, or this charge, alpha particle, is not moving through that entire 15 centimeters. So it's not moving through that entire 60 volts. So we can't use that equation for that. What we need to use is Q E, D. All right? When I set that up, I think, well, I don't know the electric field strength. Okay, is there any way that I can find that? Well, I do have the equation that volts is equal to ED, so I can take my volts divided by my distance and get my field strength. But wait a second, we just said that we couldn't use that. I know, this is where we have to keep the plates and the, in this case, alpha particle separate. So when we're talking about the plates and the voltage, all right, and that's creating this field strength that we can see with these lines, then we have information. We have the 15 centimeters and the volts. So that 15 centimeters is talking about the distance represented here. I'm going to circle that in red and circle this in red. Okay? Now, the distance that it moves is different. Let's put that in another color. Let's put that let's go with green here. The distance here that it's going to move that alpha particle is this D. And that is a thing that's very easy to get confused. And fair enough, they're both the same symbol, but those are talking about different distances. The plates creates the field strength, and then how far the particle moves is related to its potential energy in this example. Okay, so I'm going to put those two together now and say that 8.99 times 10 to the negative 18 joules is equal to Q. Now I'm going to write the voltage divided by the plate separation. So volts divided by D. Let's put it in red just so we're reminded that that's the plate separation in red. And now we can have that term for how far the alpha particle is going to go right here. I'm going to put that one in green. So it might look, you have times D divided by D. I can cancel them and just get QV, but those are different distances, and that's probably the hardest thing about this example. Okay, so now let's solve it. I take 8.99 times 10 to the negative 18 joules. Going to divide by my Q, which was the charge on the alpha particle, plus 2 of those elementary charge of 1.6 times 10 to the negative 19. So I've got rid of the Q. Now I'm going to also divide by volts. Let's make this a little bit longer. Put volts on the other side denominator as well, which is 60 volts. Now I'm going to multiply this D here by multiplying that. Remember, that's the red one. So 15 centimeters times 0.15 meters. And that should leave us with the green D, or the distance that it's going to move in the plates. And I get an answer of 0.07024. So converting that into centimeters, I divide by 100, and that's 7.0. I think I only had 2 digits, so 7.0 centimeters here for the answer, which is almost halfway through the plates. Okay, so that's it for today's video. I know it's kind of a complicated example. Make sure you go through that and, again, really enforce the idea of when we can use those different formulas and those different distances. Let me know if you have any questions, and you can ask me them in the live time. Thank you for watching this video, and I will see you in the next lesson.